everyone, we're going to be doing lab 4.2 with Newton's 3 laws of motion, and we're going to have a good time with some stations today. Oh boy, here's Jeff. Jeff, we're not doing this again. We have a lesson to teach, okay?
But I thought we might play a game first.
Mommy-o!
Skylar? Hello everyone, welcome back to this is McAllister's Science Station. We are going to be working on the laws of Sir Isaac Newton today. And Sir Isaac Newton described 3 laws that relate to force and motion. Please remember from our previous lessons that force is a push or a pull, and all forces have size and direction. And again, the good old unit for force is the Newton. So the story goes that Isaac Newton was sitting in his garden and an apple bonked him on the head, and he came up with a theory of gravitational force. That is definitely an embellished story by generations of telling it, but the idea is Sir Isaac Newton was wondering, why did the apple go down and not go up when it came off of the tree stem? So the 3 laws of motion that Sir Newton described. Law number 1. Objects at rest stay at rest. Objects in motion stay in motion. Law number 2. Force equals mass times acceleration. And law number 3. For every action, there is an equal and opposite reaction. So please note that in a Newton's cradle, all 3 of these laws come into play. And I have one at my desk, which I would have shared with you in the classroom, but because we can't, I have a few examples of them online that I was able to identify with this law. So let's take a look at those.
Isaac Newton observed that for every action, there's an equal and opposite reaction. When we pull one of these pendulum spheres back, it pushes one sphere up on the other side. If I pull 2 back, 2 go up on the other side. And as you might expect, if I pull 3, 3 go on the other side. The middle one goes back and forth. For each action, there's an equal and opposite reaction. This demonstrates one of Newton's laws, and by long tradition, this is called Newton's pendulum. I wonder what Isaac Newton called it.
Okay, so Newton's first law, we're going to look into that. And again, it says an object at rest stays at rest versus an object in motion is going to stay moving. And that's only if it's acted upon by another force. If it's acted upon by another force, it could stop motion. And if you're thinking what that force is, the force of friction is going to prevent that moving ball and other moving objects. In terms of the first law, the term inertia has to do with the tendency of an object to maintain its state of motion or rest. So a nice example of that is if you're in a car going 60 miles an hour, you're going to keep on moving with the car. You are moving in the car. Both of you are traveling, or you're traveling in the car. Versus if the car unfortunately crashes into something, the car stops. But you, because you are moving at that same 60 miles an hour, are going to collide out of the car if you're not wearing your safety belt. So examples of Newton's first law, again, the car stopping suddenly and you strain against the seatbelt so that you don't come out of the car. Or the difficulty of pushing a bus that won't start, meaning that it's stopped, it doesn't want to move. It's wanting to stay put. So I have a worksheet, Newton's first law. There's some nice examples of this law in place, 1 through 4. One of them is a person lets go of a hammer. Why does it fall? Number 2, a marble is sitting motionless on a table. How can you make it move? Number 3, a cube sliding across the table slows and stops. Why does it stop? And number 4, what is another example of Newton's first law? So I'd like you to fill this in for me. And again, everything that we have talked about today and Wednesday is due on Friday. Newton's second law. This is a fun one because it combines a few factors into a formula. This formula is force is equal to mass times acceleration. And so we're looking at a baseball player here. You can see that there's a lot of force exerted on the ball. The more force, the more acceleration, faster that ball is going to go, hopefully out of the park. So hitting a softball, the harder you hit, the faster the ball goes. Same thing with any sport, really. Football player kicking a football. So many different examples there. But again, the formula here, force equals mass times acceleration. F is equal to ma. Very familiar formula as you get into high school as well. So much so that people use it in a fun t-shirt setting of may the mass times acceleration be with you, meaning the force. There's Baby Yoda. Hi, Baby Yoda. And of course we have another formula pyramid. Remember, if you cover one up, you do the math for the other two, you get that variable. So if you cover force, force is mass times acceleration. If you want mass, it's force divided by acceleration. And if you want acceleration, it's force divided by mass. And using that formula, I'm going to ask you to complete this worksheet, Newton's second law, using the mass times acceleration equals force formula to do questions 1 through 5. We also have another series of practice questions, 1 through 8. I'm going to ask you to do those as well. Again, very straightforward using the formula, just plug in the appropriate variable, and then this again will be all due on Friday. All right, finally, Newton's third law, which I like the best. For every action, there is an equal and opposite reaction. Forces always come in pairs. So here we have an example of a ball bouncing on the floor and going back up. We have a balloon that's being released of the air. The air is going in one direction, the balloon goes in the other. You might have experience with that. And here's a nice example just showing the ball bouncing down, hitting, it looks like a rubbery surface. The rubbery surface is going to react to that action of the ball bouncing on it, and the ball bounces right back up. Here's some other examples of Newton's third law. We have one person who is trying to, jump off a boat. The person goes one direction, the boat goes the other. We have a person who is pushing a refrigerator, like we saw in our simulation of force and motion. The refrigerator and the person are going in one direction, but there's a force of friction there that's going to prevent all the possible motion. And then we have a car who is driving in one direction, but again, there's that drag or friction against that force. So you would need to, again, calculate those vectors to identify what that motion in terms of Newton's is. And then we have a series of questions for Newton's third law. Please note that I'm looking for you to identify the following. Number 5, a student is holding a marble in his hand. What are the equal and opposite forces that are acting on it? Number 6, a bag of marbles is hanging motionless on a spring scale. What prevents the bag from falling? Number 7, when gas particles rush out of the nozzle of a rocket downward, why does the rocket move upward? And number 8, what is another example of Newton's third law? Okay, so just to recap, objects do not change their motion unless a force acts on them. And the more mass an object has, the more inertia it has. Again, whether it's going to stay put, like a big bus in a parking lot, or if it's going to keep on going, like a car that's driving down the highway. So just know that we are going to have homework on board for this in terms of a reading on your FOSS-Web for this Gravity and Kinetic Energy textbook. There is a series of questions on pages 45 through 49. The think questions are at the end, and there's just two. I'm going to ask you to complete those after you read the information about the Newton's 3 laws. All right, so this is the part where we're going to get into stations, which we would again have done in groups at school, but I'm going to mix it up a little bit. I'm going to do the station and ask you to identify which of the 3 laws of Newton the station applies to. So if you need to look back in your notes to identify the 3 laws as we look at the station, that's completely fine. If you want to pause the video, that's fine too. Okay, so let's go to the first station. There's a total of 8. The first station says, place a cup of water on the table and put a piece of cardboard on top. All right, let's do that. Lots of materials today. All right, then we're going to put the roller on top of that. This means Mrs. McAllister has toilet paper. And then we're going to put a ball on top of that. Okay, so predict what will happen to the ball when the cardboard is removed. And as quickly as we can, we're going to remove the cardboard and make our observation on the ball. That's what we're concerned about. And then once we do that, which of the 3 Newton's laws does this apply to? Okay? All right, so let's see what we can do here. Okay, so if you need to rewind and go back to see what the ball did, obviously it's in a container of water, which was right below the cardboard. What happened to that ball, and which of the 3 of Newton's laws does this apply to? Okay. All right, let's go to station number 2. Station 2, place a penny in a bucket, hold the bucket by the handle, and swirl it around in circles a few times. Here's a bucket. Here's a penny. I'm going to just swirl it around on my wrist, and you're identifying what is happening to the penny. Okay, here we go. All right, so then which of the 3 laws does this station apply to in terms of what the penny was doing? Station number 3. Place a note card on the top of a cup. Place a penny on top of the card. Thankfully, I have a nice penny duck here. Plenty of pennies. All right, predict what will happen when the card is rapidly removed. So this is another example of station 1. Hint, hint, it will be the same law. All right, here we go. Pull the card as rapidly as you can. Predict what will happen to the penny. Aha! And you're welcome to do this at home because it is 100% safe. Absolutely. So we observed the motion of the penny. Why did that happen? Go ahead and record that on your data table. Station number 4. Place a penny near one end of your table. All right, more pennies. Here we go. Use your finger to propel the penny towards the other end of the table and trying to get it to the edge of the table. As close to the edge of the table as you can. Ooh, that was a good one. All right, see if you can do that too. And then what law does this station apply to? Station number 5. Set up the car so that it is at one side of the table. Here's a little Snoopy. Push the car and watch what happens to the hippo. All right, let's do it. All right. Now we want to push Snoopy harder into the hippo. There we go. All right, observe what happened to Snoopy and the hippo. One more time. That was a good one. And which of the 3 laws of Newton does this apply to? Station number 6. Place a marble on the top of a track. Here's a track. Here's a marble. Place another marble on the bottom. This is a marble on a stand. And then identify what will happen to this one when we put this marble on the ramp and let it collide. What do we think will happen? All right, release the top marble and let it collide with the second marble. Ooh, good. Let's do that one more time. Okay. Please tell me which of the 3 laws of Isaac Newton this station applies to. Station number 7. Put the propeller on the stand and let go of the propeller to see what happens. Identify what is moving the propeller forward and what is moving backward. So here is the propeller, just so you know what it looks like. It's on a twirling mechanism. I'm going to release it. Try that one more time. Ooh, that was good. Let's do that one more time. It's pretty fast. There it went. Okay, so what happened to the propeller? And in terms of what was moving backwards when we pulled this string. What law did this apply to? And finally, station number 8. Move one pendulum ball back about 2 feet. Let it fall into the other ball and watch what happens to each ball during the collision. Here we have 2 of the pendulum balls. We're going to let one stay stationary, and we're going to, again, about probably 1.5 feet up, we're going to release it and see what happens. Let's do that again. Okay, go ahead and tell me what law that station applies to. So in terms of the correct answers, station 1 through 3 applies to Newton's first law. Stations 4 and 5 apply to Newton's second law. And stations 6 through 8 apply to Newton's third law. So please note that we are going to watch a few videos regarding Newton's 3 laws right now. One of them is a study jams, and one of them is going to be a fun interactive with pendulums. I hope that you enjoyed this video, and if you have any questions, please feel free to contact me via email or meet us on Google Meet on Monday, Wednesday, and Friday at 11 o'clock. Have a great day.
Ow.
Zoe, watch out!
Ouch!
Hey, are you okay?
Yeah. Oh, hard bench. Guess I wasn't looking.
Now that's what I call action and reaction.
Action and what?
Action and reaction. It's Newton's third law of motion.
What?
You know Isaac Newton, the gravity guy? He realized that for every action, there is an equal and opposite reaction.
Like, if I run into you, you run into me at the same time?
Pretty much, but there's more to it. Okay, so when you bumped into me, you applied force or pressure against me.
Yeah, sorry about that.
According to Newton's law, my body pressed back against you with the same force.
Come on.
We both felt the same force because the forces from our bodies pressed in opposite directions.
Yeah, but if we hit with the same force, how come only I got knocked down?
Good question, champ. It's all a question of mass. How much matter is in something? First of all, who has greater mass, you or me?
Is that a trick question? You, obviously.
Well, according to Newton, when two objects with different mass collide, they'll accelerate at different rates.
Accelerate?
Change their speed and direction.
So, even though their forces are the same, one will accelerate more than the other?
You got it. The object with smaller mass will accelerate more.
Smaller? That would be me. So I fell, and you didn't.
Hey, come to think of it, the same thing happened with you and my soccer ball. You hit each other with the same force, but the soccer ball went flying.
I got it now. Because my mass was bigger, the ball accelerated more. How about when a baseball bat hits a ball?
Yep, both objects hit each other with equal force in different directions. The ball goes flying because its mass is smaller. The way the bat is moving when it hits can make the ball go in different directions.
And what happens when two things that are the same mass collide? Like two pool balls?
Well, what do you think?
Well, they hit each other with the same force, and the forces press in different directions, so they have the same acceleration?
Yeah.
Wow, this action and reaction thing is a little complicated, but I think I've got it. Newton's third law says that for every action, there's an equal and opposite reaction. That means that when two things collide, they press with the same force in opposite directions. That's why you and I both felt it when we bumped into each other. And when the objects have different mass, like we do, they'll also have different acceleration. The object with smaller mass, in this case me, will speed up or accelerate more.
And she scores. Now that's what I call a smart reaction.
What can I say? I'm just a genius in full force.